Beautiful. Okay, so we are still stating our given. So we have P1 is open to the atmosphere, V1 is a large reservoir. If we set 2 to be our datum, so at 2, then we have P2 is 0, again, open atmosphere. V2 is 0, again, large reservoir. In this case, Z2 will be 0 and Z1 will be 50 feet, okay? So now I want to bring it back to the question. So it says, water flows by gravity from one lake to another. So water flows, the water, by gravity from one lake to another at a steady rate of 100 gallons per minute. So Q is 100 gallons per minute. And it says the first part is what is the loss associated, in available energy associated with this flow, okay? So what is our head loss, okay? Now, in this first part, it says water flows by gravity. So how does water generally flow by gravity? It always flows downwards. So part 1 is going to be water flowing down via gravity, which means that we're going from 1 to 2. And also, in this part, there is no pump, okay? No pump. Now, that means our energy equation becomes 1, from 1 to 2 is P1 over gamma V1 squared, sorry, alpha 1, over 2G plus Z1 plus our pump, which we don't have yet, is P2 over gamma plus alpha 2 V2 squared over 2G plus Z2 plus loss plus turbine, which we don't have, okay? Now, my favorite part is always crossing everything off. That goes away, that goes away, that goes away, that goes away, and that goes away. And it is that simple that Z1 is going to be equal to our head loss. So we have our loss. Now, in the second part here, it says that if the same amount of loss is associated with pumping the fluid from the lower lake to the higher one at the same flow rate, so same Q, but now we have a pump. So now we're going this direction. Do you see that?
Yeah.
Okay. Estimate the amount of pumping power required. So pumping power means W dot. That's what we're solving for now. Okay. So part 2 is solve for W dot of the pump. And in this case, we are going now from 2 to 1. So we have to set up our equation again. So P2 over gamma plus alpha 2 V2 squared over 2T plus C2. Now we have a pump. Is P1 over gamma plus alpha 1 V1 squared over 2G plus Z1 plus our loss plus, and we do not have a turbine, so that goes away. These things still go away, right? Now, in this case, we have my datum is at 2, right? So Z2 goes away and end up with HP is Z1 plus HL, which this is going to be 50. This is 50. So HP is 100 feet. Okay? All right. So now we have our other equation that we can use, right? Where HP is W dot P over gamma Q. Here, I am already assuming my efficiency for the pump is 1. So, okay, we don't need to worry about that. Okay. Now, the only thing left to do this numerically would be to convert our flow rate And let's see. And then we can solve for WP. So let's do a quick convert. So conversion of Q. So Q is 100 gallons per minute. And we're going to convert this to cubic feet per second. So I have 7.48 gallons in 1 cubic foot. And in 1 minute, we have 60 seconds. Can someone quickly give me a calculation for Q?
0.223 feet cubed over seconds.
223 feet cubed per second. Perfect. I see confirmation already. All right. So then W dot of the pump is going to just be HP gamma Q, which is 100 feet multiplied by gamma, 62.4 pound force per foot cubed, multiplied by Q, 0.223 feet cubed per second. So what is my W dot going to be?
1391.52 pound force over seconds.
Beautiful. Now, is that useful to us? No. We have to convert this to get horsepower, right? So then we're going to convert 550 foot-pound force per second is 1 horsepower. So W dot is going to be approximately 2.53. Yes, okay, horsepower. So that would be my answer. And according to the key, that would be value A. Okay. Now, does anybody have questions on this solution?
I have a question on the efficiency. When is it not 1?
It has to be given in the problem statement that the pump was either operating at efficiency, like at 100% efficiency. Like let's say you had to solve the problem that way, and then it said over time, this is the work that it actually produced. And so then that's when you would get an idea of the efficiency parameter. And you would either have to do it again or you would just solve for efficiency. But sorry, there has to be something given in the problem statement that the system is not behaving efficiently. And usually it's the value itself. It'll give you a value of like 0.7, 0.9, or it'll say, like I said, it'll say that the work was this, so that's like perfect efficiency, and then became this, and that's how you solve for that efficiency parameter.